All right, we'll start the session. Once again, welcome to UNS EduTech's physics demo class. Myself, Sanal Mohanan. I'm basically a mechanical engineer. Then I did my master's in applied mechanics with a specialization in heat transfer, heat and mass transfer, and fluid mechanics. And I will talk about UNS EduTech. I'll give a brief introduction about UNS EduTech. Some of you may already know about us, and if anybody else is new here, I will introduce you about UNS EduTech. So UNS EduTech is basically a team of graduates from, a team of graduates from and those who are doing degree from IIT Madras. So we are a group of students who are doing undergraduates, graduates, like postgraduates and PhD scholars. We are into developing teaching methodologies, like basically based on activities and a lot of animations we used to make, so that the teaching will be more intuitive and students will be able to understand the concepts in a in-depth fashion, so that students will be able to retain the concept for a longer duration. And you know that mostly in India students are studying like mostly by hearting, or we call it rote learning, and that is happening for decades, and we are trying to revolutionize that part. Like now exam is not only our objective. We'll be focusing on concept building first, then automatically exam you will be able to score well. That is our idea. And we have a small R&D team in Chennai, in Velachery, and we are developing a lot of experiments, a lot of animations, a lot of teaching methodology, or we call it pedagogy. So we are into that, and we are dedicated to share the teach concepts in a in-depth fashion. That is our introduction. The rest you can go to our website, you can understand more about us. And today I will be giving a demo session like from a topic in physics, +1 physics. I know that most of you are going to, like all of you are going to +2 in couple of months. So this part you can take it as a demo session, and all of you might have covered this topic in school already. So still we will show you, it's a kind of, we are showcasing how we are teaching. So take in that sense. So today we'll be covering kinetic theory of gas. Kinetic theory, we are not going to deal with the details. We'll be covering a small topic called gas laws, okay? And I will try to connect you with, first I will show you some demonstrations, then I will explain the laws, the gas laws. Then I will take you to the practical applications or whatever, wherever is applicable. Then I will show you the problems. Previous year few problems also will be solving in the class. Okay. So I hope all of you are able to hear me. If anybody have any issue, please drop your comments in the chat box. And one more thing, if anybody is having doubt, since this is a live session from our studio, not a Zoom class in a normal way, like we have limitations in answering questions immediately. So we'll be allotting 10 minutes at the end, so that you will be able to answer, like you will be able to clarify your doubts. Okay, I will inform you at that time. You can ask your doubts, you note down your doubts, or you can drop your comments in the chat box, so that I will be able to answer. Okay, anyway, thank you once again. Welcome to our session. So now we are going to discuss mainly about gas laws. Gas laws is coming under the topic, kinetic. There is a chapter, thermodynamics, heat and mass transfer. Heat and mass transfer have 3 different topics. First one is calorimetry. Then like mass transfer, that thermodynamics part is there. Then kinetic theory of gas is there. So in the kinetic theory of gas, there is a section called gas laws. So we are going to deal with that topic today. In gas laws, that mainly there is one important law called Boyle's law. So all of you may know that Boyle's law. So there is a relation between pressure and volume. So first I will do one thing. I will show a simple demonstration. Then I will show you what exactly we are talking about. Then we will go back to the board, so that you will get a very good picture. So in order to demonstrate that, I have a small setup here. So I have a tank here. See, I have a glass tank here. Okay, inside the glass tank I have a balloon. Okay, and right now the pressure inside is atmospheric pressure. All of you have a very good idea about pressure now, because you already covered the properties of matter. So you already know about the pressure. So pressure is nothing but force per unit area. And right now, if the system is on the surface of Earth, if it is not enclosed, even if it is enclosed, if there is no other setup connected, inside pressure will be atmospheric pressure. And that certain amount of, for example, if you are taking a balloon, something like this, balloon is here, outside I have another balloon. So, certain amount of gas is involved, like gas in the sense, whatever atmospheric air is trapped inside this balloon. Okay. So, certain pressure is there, certain volume of air is there inside. Now, what I am going to do is, I have a vacuum pump here. Vacuum pump is a mechanical device. You can see that here we have a vacuum pump. See, this is a vacuum pump. Vacuum pump means once you switch on this, it will take out all the air from this chamber, this glass chamber. Okay. Now, if I switch on this, I told you, it will try to suck out all the air from this tank. And I will show you that. I am not explaining what is going to happen, and all of you watch this carefully. And I am going to switch on the pump. You just focus only on the size of the balloon, what exactly is happening. I will explain you slowly once I finish this demonstration. All of you listen carefully. Okay. And you should be focusing on the size of the balloon. Okay. I am going to switch on the pump, vacuum pump. You can see that balloon size is, see, I will release the gas now. See, the size is going back to old size. I will show you once again. Please listen. I am going to switch on again. You see the size of balloon. See, I am going to release the gas again. Release in the sense I am introducing gas into the system. Okay. So, what is happening here? All of you seen that I told you vacuum pump is a device which can take out the air from our chamber. Okay. So, here what we are doing, I will explain you what exactly we did here. So, we have a chamber like this. Okay. Inside the chamber, there is a balloon, and this part we are connecting to a vacuum line so that air is taken away from that location. And that because of that reason, see, previously outside pressure was P0, the atmospheric pressure, and inside pressure was also P0. Now, when you are taking out the molecules one by one, we are taking out using that pump, we are taking out, what happened, the pressure become P or P final, it will reach some pressure P final, and P final will be always less than P0. So, that initial V initial was the volume initial of that balloon. Now, when you are taking out the air or reducing the pressure, since you are sucking out the air, you are reducing the the pressure you are reducing, then what happened? Volume final will be greater than volume initial. That means, since you are reducing the pressure in the chamber, what is happening? Expansion is happening. The volume, the gas is expanding, or we can say the volume is expanding. So, basically this is an inverse relationship between volume and pressure. So, that here you have to remember that the temperature of the system we are maintaining constant. Okay. T is equal to constant. See, if you are in the room, if you are doing the experiment, that T is not changing. So, T is constant, and at a constant temperature, if you are changing volume, the pressure also will change, or if you are changing pressure, volume will change, and that is an inverse relationship. This relationship is called Boyle's law. In a concise form, we used to say that this is Boyle's law. So, if you are going to this graph, you can see that here I am going to show the pressure versus volume graph I am plotting. Okay. In this case, see, I have three different cases I am showing, T1, okay, then T2, so this is T2, and T3, three different cases are there, and three different temperature the graph is shown. So, you already know that based on that what we observed, that P proportion to 1 by V. If you are reducing the pressure, the volume is increasing. That is what you observed in Boyle's law. Okay. Now, we can write down, see, in any proportionality relation, you can write down simply PV will be equal to a constant we can write. This law is called Boyle's law. Okay. So always remember PV is equal to constant or P proportional to 1 by V is called Boyle's law. Okay. Now we are going to next law, that is nothing but what happen if you are heating up a system. I mean if you are heating up a system, enclosed air. See, I will show you the system before going to the experiment. I will show you another experiment. See, I have another chamber like this. Okay, I will show you now, and I am going to connect a balloon to the tip of that, and I am going to provide some heat to the system. So you know that previously lot of molecules are there in the system. Okay, and when you are providing additional heat energy, you know, expansion will happen, and as a result, you know, this volume will be increasing, or there is a relationship between volume and temperature at constant pressure. Constant pressure in the sense, you know, if you are allowing to expand, if you are allowing this gas to expand, so the pressure in that system will be maintained, or the same pressure will be there, initial and final pressure will be same, or we can say that pressure will be constant. So at constant temperature, sorry, at constant pressure, you know, volume proportion to temperature. This law you already know. Anyway, we will do the experiment, then we will go back to the law again. See, look here. In order to do that, I have another system here, like a flask I have. See, empty flask, nothing is there. In the flask I am going to connect a balloon. To the mouth of this flask I am going to connect a balloon. See, I have a balloon here. I am going to connect this balloon to the, see, something like this. You can see I have connected a balloon to this flask. Okay, and I have a burner here. I am going to switch on the flame. Wait a second. See, I am going to show that to the flask to the balloon. Look at the balloon. You can see that balloon is expanding. See, look at this, balloon is expanding. Okay, so if I switch off that, I will show you. I mean, if I open this, see, again, I will repeat the experiment for you once again. All of you see this. I am going to connect the balloon again. I am going to show to flame. Look at the balloon again. See, is expanding. Okay. So here what is happening? Just a second. See, since you are allowing to expand, that is very important. The pressure initially was P0, and you are allowing to expand the system. When you are heating up, you know, thermal expansion will happen to the molecules, and expansion is happening here, and the pressure, because of that expansion, boundary is like stretching, and as a result, you know, the pressure will be maintained. The pressure will be maintained, and maintained in the sense constant pressure will be there, and temperature is increasing, volume is increasing. Though this law is called Charles' law. So it's very simple. All of you might have studied in the school, you might have studied. If you are plotting volume versus temperature, see, this volume versus temperature at a constant pressure. So if you are taking at P1, P2, P3 different pressures, you know, different graphs will be there. That is a directly proportionship, direct proportionality. So volume will be proportional to temperature. Okay. So if you are increasing temperature, the volume of the gas will be increasing. So that is the second law, second important law, and we can write down this in a concise form. V by T will be equal to a constant. Okay. So this is called Charles' law. Okay. So two laws we studied. One is Boyle's law. Boyle's law is nothing but pressure is inversely proportional to volume. Now this is volume is proportional to, directly proportional to temperature. So two laws we studied and experimentally we verified. And one more law is there. We are not verifying that experimentally, but I will show you through an animation. I will show you that. All of you listen. Just a second. Yeah. Look here. See, here I have a chamber. Again I have a chamber and I have a system to pump in air into the system. Okay, I will show you that I am going to pump air into the system. See, look here, molecules, you can see air molecules are entering into the system. Okay. Now I have a facility here to heat or cool down the system. I'm going to, if I'm heating, you look at these values. You know, we have one pressure gauge here. See, pressure gauge as well as one temperature gauge is there. See, you look at the value, 300 Kelvin is the temperature now. Okay, almost atmospheric temperature we can say. Now the pressure, see here 33 atmosphere is there, like some other high pressure also, like it doesn't matter what is the value, but you look at the what is happening to that when you are heating up the system. So you can see that here the volume is kept constant. Okay, volume is kept constant because you know rigid boundaries are there. You are not, the system is not allowing to expand. So we can say that a rigid metallic or rigid boundary is there, and in such a system if you are providing heating, you know, the pressure of the system will increase. This is another law, we are going to that. Let us see what is going to happen when you are doing this experiment. So you can see that if I am heating the system, look at the value of pressure and temperature. All of you focus on that. Okay, I am going to heat the system. See, temperature is increasing, corresponding to that pressure is also increasing. We can see after some time the lid will break. You can see if I keep on do that, you can see lid will break after some time, it will expand. Let us see that. See, you can see that lid is breaking and gas molecules are escaping. Okay. Now let us see once again. I am going to, if I cool down, what happens? See, if I cool down the system, you can see temperature is reducing and the pressure is also reducing corresponding to that. So there is a relationship between temperature and pressure at constant volume. This law you can see is going to reach very low temperature. See, and at the same time you can see the molecules, the particles, the speed is also reducing. That is another thing that is coming in the kinetic theory of gas. You know, the velocity of the gas molecules are proportional to the temperature. You can see when you are reaching very small temperature, like you know closing the absolute zero, you can see that the molecules are almost coming to rest. Anyway, that is not our topic today. I am just showing that since it's connected. So here, when you are heating the system at a constant volume, the pressure is increasing. This law is called Gay-Lussac's law. Okay, Gay-Lussac's law is nothing but at constant volume. Let me go back to this. At constant volume, see, this is Gay-Lussac's law. If you are plotting pressure versus temperature at constant volume, you know, the pressure is proportional to temperature. So this is also direct proportion. The pressure will be proportional to temperature, or we can write down in a concise form, P by T will be equal to a constant. This is called Gay-Lussac's law. Okay, these things are very simple. All of you know about this, but we have to understand in a much in-depth fashion so that you are not by hurting. Many people will study PV is equal to constant, Boyle, so like that. But you have to visualize, you have to connect it with real life, what exactly is happening when pressure is changing, what exactly is happening to the volume. That kind of connectivity you have to build with your surroundings. Then only the actual learning will happen. Then only you will be able to apply these concepts in future in whenever a practical situation come in your life. Okay. So here you can see this is Gay-Lussac's law. Then one more law is there. See, that one is actually an empirical law. We can say that is nothing but Avogadro's law. All of you may know this. Avogadro law is nothing but equal volume. If you are taking, see, one container, same quantity, like two containers are there, both having same volume, and in one container you are taking 1 liter of oxygen, in another container you are taking 1 liter of nitrogen. In that case, you know, Avogadro law says that if the temperature and pressure, all conditions, you are maintaining same value for both container, then, you know, I will show you that. I'll add a, see, assume that you have container 1, let it be A, and container 2, let it be B, and in the container A, you are putting some gas, maybe O2 molecule is there, and in container 2, maybe N2 molecule. If both volume are same, VA, VB, and VA is equal to VB, if that is the case, and if temperature is same, okay, if TA is equal to TB, okay, and pressure A is equal to pressure B, in such case, both gases, both container will be having same number of molecules, or equal volumes of all gases under same volume and temperature, same pressure and temperature will contain same number of molecules, or number of moles will be same. That is called Avogadro's law. And in connection with that, there is a constant called Avogadro's constant. Is a very important rule. I mean, Avogadro's number is a very important constant in physics as well as chemistry. So here you can see volume per mole we are plotting against mole, or we can say the V by N will be a constant. So equal volumes of all gases under same temperature and pressure will contain same number of moles or number of molecules. That is called Avogadro's law. So now we have studied 4 laws. One is Boyle's law, Charles' law, Gay-Lussac's law, then Avogadro's law. So now we are going to combine all these laws. See, these laws are actually applying on the same gas, same volume of gas under different conditions. One is at constant temperature, I mean the first one. The second one is at constant pressure. The third one is at constant volume. The fourth one, that at the same volume, V by N will be constant, or equal volume of all gases under equal volume of all gases under same temperature and pressure will contain same number of moles or number of molecules. That is called Avogadro's law. Now the interesting part is coming. So now we are going to combine all these equations, and we are trying to develop a single equation and with a single constant, and you will get ideal gas equation. We are going to discuss about what exactly is ideal gas. That what we are going to cover now. So now you can see that if you are covering, and one more thing, see, if you are taking this is actually the number of molecule present in one in standard atmosphere. If you are taking 22 liters of gas, that at standard temperature and pressure, it contains 6.022 into 10 to the power 23 molecules will be there. If you are taking per mole, if 1 mole of gas will be containing this much volume of this much gas will be, this much number of molecules will be there. So that constant is called Na, or Avogadro constant. And now we are going to combine all these laws together. This is a very important slide. So you can see that here. See, you are going to combine first Boyle's law. So Boyle's law is nothing but PV is equal to constant. You already know that. See, PV is equal to a constant, some K. Okay, here one KB is there. There is a different constant. We are going to discuss about that. And now Charles' law, V by T is equal to constant. Okay, V by T is equal to constant. Then third one, which one is that? Gay-Lussac's law, P by T is equal to constant. Okay. P by T is equal to constant. Then V by N is equal to constant. Here, look here, we are using capital N. The capital N is usually total number of molecules. Small n will be number of moles. You studied in basic concept of chemistry, you studied that. And the capital N will be the total number of molecules. Okay. Now V by N is equal to constant. That is nothing but Avogadro's law. V by N is equal to another constant. See, these are different constants. Okay, don't think that all are same constants. Now, what do you mean by this? If you are writing the equation in a single form, PV by Tn is equal to, you are getting a constant. What do you mean by this? This is called ideal gas equation. See, PV by Tn is equal to Kb. So PV by T into N is equal to Kb. This means that if you are taking a container, if you are taking the balloon itself, in the previous case we have shown the balloon. If you are taking the balloon, you can see it contains certain amount of volume, certain pressure is there, okay, certain temperature is there inside, okay, certain number of molecules are there. In this case, in reality, lot of all the species are available, like oxygen is there, nitrogen is there, hydrogen is there, argon, krypton, lot of things are there. So that if you are, for this particular case, if you are taking the pressure of that balloon, taking the volume, then taking the temperature, number of molecules, if you are doing this particular math or particular ratio, if you are trying to estimate, you will get a single constant, and that constant will be like that is a invariable, or it won't change with if you are in any different case. If you are expanding, some temperature change will happen. In that case, corresponding to that, other quantities will change. So if in any situation, if you are taking the ratio, this particular quantity, this ratio will be a single constant, and this constant is called Boltzmann constant. Okay, Boltzmann constant. Now remember, this ideal gas is applicable only for a range of temperature and usually for low temperature and pressure, and very high superheated condition or very high pressure is not applicable. That is why we call it ideal gas equation. That is also very important, and we will be discussing once we finish this, we will be discussing about ideal gas. What exactly is ideal gas? That part we will discuss. Okay. So here we will discuss about the Kb. What exactly is Kb? So you know that here, just a second. See, Kb is actually a constant called Boltzmann constant, and that constant value is 1.38 into 10 to the power minus 23 joule per Kelvin inverse. That is a universal constant. So whenever you are taking for a gas, for a given amount of gas, PV by Tn will be giving you the Boltzmann constant Kb. And you may be familiar in another form, PV is equal to nRT. That equation you are familiar, but this is just another way of expressing that, and there is a relationship between R and this Kb. R is nothing but universal gas constant. Okay. Now we are going to that equation, and we are going to establish the connection between universal gas constant, then Boltzmann constant, and Avogadro number. So that part is very important in exam perspective. It's very, very important concept. All of you please use. And one more thing, you know, especially people make mistakes in this. You know, students usually make mistakes in while putting values. You make sure that if you are putting pressure in SI units, everything should be in SI unit. In certain conditions, if it is cancelling out, you can use some different unit, but you know, normally if you are doing a problem, always use SI unit. And remember, most important thing, temperature should be always in Kelvin, never put degree Celsius. You know, degree Celsius and the angle degree doesn't have validity in calculations. You know, in angle calculation you have to use radian, and in temperature calculation you have to use always in Kelvin. That's a very important rule. So you may be familiar with, you know, PV is equal to nRT relationship, and there is a connection between PV by Tn is equal to Kb. So let us go to that. So now you are familiar with this equation, PV by T is equal to nRT, where n is nothing but number of moles. Now what is number of moles? N will be equal to the mass of the gas divided by the molecular mass of the gas. This value is called number of moles. So PV divided by T will be equal to nR. This equation is also called ideal gas equation, and R value, R is called universal gas constant, and its value is 8.31 into 8.314 in joule per Kelvin inverse mole inverse. Always remember, this different system use different value of R, but always you can, if you are by hearting this particular value, we can keep that value in SI unit. This is in SI unit. Sometimes you use in kilojoules, and you know, you don't confuse that time. So all the values you have to keep in mind. So here it is in mole, and sometimes, you know, some other units will be there, some degree Celsius also will be used. That doesn't matter much, you know, anyway that will be same value, you know, per degree or per Kelvin, it doesn't matter much. So anyway, you know, now we have two equations, PV is equal to nRT, and see, first equation was PV by Tn was equal to Kb or Boltzmann constant. Now the second equation is PV is equal to nRT. So there is an important relationship between this Kb and R. You can see that if I am dividing this, or if you can write down this, this equation, the equation 1, we can rewrite in another form. See, we can write down PV will be equal to T into N into Kb, you can write down. Okay. Now if I am dividing this ratio, you can see that if I am dividing this part, see what all things will be cancelled out. See, T will be cancelled out. Okay. So you know, PV will be cancelled out and T will be cancelling out. Remaining, how much will be there? This will give you, see, this implies NKB will be equal to capital N into Kb will be equal to N into R. Remember, if N is equal to 1 mole, see, Avogadro number is nothing but the number of molecules in 1 mole of gas. See, in 1 mole of gas, you know, if N is equal to 1, that is important point. If N is equal to 1, then you know 1 mole of gas will contain, you know, that then N will be equal to Na or Avogadro number. Okay. So here you can see that here N will be equal to Avogadro number, and here you can substitute that value, or you will get, you can see that, see, Na into Kb will be equal to n into, or we can say n is equal to 1, or we can say Na into Kb, the Boltzmann constant, will be equal to R, we can say. Okay. Now we can say that here Kb will be equal to C, or we can say Kb will be equal to R divided by Na, we can say. Okay. So here the idea of Boltzmann constant is nothing but the universal gas constant per Avogadro, per molecule or universal gas constant per molecule is called Boltzmann constant. That relationship is very, very important. We can say always Kb is equal to universal gas constant divided by Na is a very, very useful relationship in terms of competitive exams. I mean, if you are preparing for NEET or JEE, this equation is very, very important. Okay. So I hope all of you understood the concept thoroughly. Now we have to discuss what exactly is ideal gas and what exactly is real gas. So real gas is nothing but whatever we are seeing every day, the gas around us is real gas, but this real gas will behave as ideal gas in certain conditions, and we have to understand that what exactly is ideal gas. See, ideal gas means we are considering the molecules as individual particles, and they are massless point particles, or it is not occupying any volume. We are assuming that these molecules are point masses, okay, and there is no interactions between them, okay. There is no interaction in the sense electromagnetic interaction or some kind of attraction, repulsion, friction, these kind of interactions are not there, but only interaction possible is the elastic collision. Elastic collision in the sense during that collision in work energy you studied in momentum conservation chapter, you might have studied elastic collision. If two bodies are colliding, if entire energy is if that is reflecting back, or if energy loss is not happening, in that case it's called elastic collision. And we are assuming that in ideal gas only elastic collision interaction is happening, and there is no the particles are not occupying any volume, individual particles, not a collection. Individual particle is a point, like massless point, or we can say point masses, and it's not occupying, and there is no interaction between them. So that is the idea behind ideal gas, and when there is no interaction between them, it behaves in a particular fashion. So that kind of gas are called ideal gas. And real gas, at low temperature and pressure, gases will be behaving in that fashion. That is why we call it ideal gas. But in other cases, at high temperature or high pressure or low pressure, very low pressure, in that case it may not be behaving as ideal gas, and these ideal gas equations are not valid. The gases may not be obeying this ideal gas equation. So such gases are called real gas. So that is the main difference between ideal gas and real gas. Okay, I hope all of you understood the concept thoroughly. Now we'll do one thing. We'll do a problem. Before going to that, see, basically UNS EduTech is dealing with active. We are trying to teach in a different way. So you might have seen that we are showing something and we are showing the animation. So we are trying to involve you in the process so that you will never forget the concept. That we call it active learning methods, and you will be able to score well in exams if you are studying like this. And moreover, you will be able to think yourself. Your independent thinking skills will go up. You will be a true innovator rather than just by hurting for exams and scoring marks. Okay, so that is the most important thing. And for decades, our Indian students are suffering from this habit of rote learning, and we are trying to revolutionize. We are trying to change that. That is our mission. So I hope all of you understood that. Okay, fine. So here, sorry, we'll do one thing. One previous year question we'll do is a medical 2000. I think it's an old APMT question before NEET. Before NEET's arrival, this question was taken from 2004 medical, and I will explain the question. All of you try to do this answer. It's a very easy question, direct question. You can do this. Try to do that and drop your answer in the comment box. Okay, and please do fast. Like we will be giving a gift for those who are commenting first, and please do that. Do in that competitive sense. You do that. So I will explain the question, and I will give you maybe 1 minute or 1.5 minutes I will give you, and try to answer this question. Okay, so here the equation of state of 5 gram of oxygen at a pressure P and temperature T when it is occupying a volume of V will be, the state equation we have to write down. The state equation, you know, PV is equal to nRT. So you have to write down, based on the given condition, you have to write down the equation. Try to do that. I will be waiting for 1 minute, then I will come back. Okay, so welcome back. So one person answered the correct answer, but I don't know the name. I can see only one K there. Okay, you can spell your name in the chat box. Otherwise, I cannot like tell your name. Yeah, Gayatri is also answering option A. Congrats. So first congrats go to that K. Sorry to say that, but we don't have a name. Okay, so Pavana. Okay, Pavana. All right. Congrats, Pavana. So thank you for that. Anyway, we'll see that what is the, you know that, see, basically PV is equal to nRT. PV is equal to nRT, you know. Okay, this is the state equation, and you know that here P is given, temperature is given, V is given, and 5 gram of oxygen is given. See, basically only thing is you have to find out the value of N. You know that N is nothing but the mass of that air, whatever gas you are using, divided by molecular mass. You know that molecular mass of oxygen is 32, 5 gram is there, 5 divided by 32. 32 means 1 gram of oxygen will weigh 32 grams. That is the idea. That is the molar mass of oxygen. So 5 by 32 will be the answer. So N will be 5 by 32, or we can write down PV is equal to 5 by 32 RT we can write down. So if you know the simple concept from chemistry, you can answer this. So the right answer is PV is equal to 5 RT. Okay. So next one. Yeah, before going to that, you know, we wish to share one information. We have a platform called Exam Grid, where you can practice a lot of MCQ tests for NEET and JEE, and you can take regular weekly or monthly mock test you can take, and you will be getting the result immediately in SMS, and you will be your progress will be recorded in the back end. So you can evaluate the progress, and the solutions are also there in that. Once you do attempt the test, all the solutions will be coming there. Okay, so that platform you can try, examgrid.com, that also you can try. So before going to that, before going to the next one, yeah, this is again a 2015 medical problem. I'll explain this. Try to do that. See, all of you try seriously. Don't be lazy. Try the solution. Okay. So two vessels separately contain two ideal gases A and B at same temperature and pressure of the pressure of A being twice that of B. There is a connection given as PA will be equal to 2 times of pressure of B, that is given. Under such conditions, the density of A is found to be 1.5 times. The density is rho. So rho A is 1.5, or we can write down 3 by 2 times rho B, that is also given. Then the ratio of the molar weight of A and B, that is a question. So what is the ratio? MA divided by MB, that is a question. So try to do, it's a 2015 medical question, try to solve the answer this based on ideal gas equations. I will give you again 1 minute or 1.5 minute, 1.5 minute. Okay, congrats Pavana and Gayatri. Again, Pavana answered first and followed by Gayatri. Congrats, thanks for that. Thanks for the attempt. So let us see that how to solve. Others, please listen. See here, you can rightly use the PV is equal to nRT equation. See, PV is equal to nRT. Okay. Now you know one information. You know that density is defined by, what is the equation for density? Density is equal to mass by volume. And you know that the N will be equal to mass divided by molecular mass. If you are dividing that, if you are applying that, you can see that if I am substituting the value for N, and you know that PV will be equal to, N is nothing but M divided by molecular mass into R into T, I can substitute. Okay. Now here M by M, see M by V value you already know, that is nothing but rho. So M by V will be rho, or we can write down P will be equal to rho RT divided by capital M, where capital M is nothing but the molar mass. See, here all the information are given here. You can directly substitute and you can find out the ratio. See here I am rubbing, I will write down this again, just a second. See here, let us write down this equation for both case. You know, we can write down PA, first we can write down PA will be equal to, or PA into MA I can write down, okay. PA into MA will be equal to rho A into R into T, because R is a constant and temperature is also given, because given that at same temperature is given. So this will be the equation, the state equation for the first one. Similarly, the state equation for the second one will be, you know, you can write down PB into MB is equal to rho B into RT we can write down. You take the ratio, if you're taking the ratio, this RT will be vanishing and remaining what all things are there? PA divided by PB will be or into MA divided by MB, that is the unknown quantity which we are trying to find out, that will be equal to rho A divided by rho B. And let us go back to the given condition. What is given? The pressure will be equal to PA is equal to, given that pressure A is equal to PA is equal to 2 times of PB, and given that rho A is equal to 3 by 2 times rho B. These two conditions are given. So PA by PB I can directly substitute is 2. This value will be equal to, see this value PA by PB is equal to 2 from here. So or we can say, and rho A by rho B is 3 by 2, or this we can equate to 3 by 2, and here 2 will be coming, this quantity will be replaced by 2, and MA by MB will be equal to 3 by 4. This implies that, okay, MA by MB will be equal to 3 by 4, and 3 by 4 is the right answer. Option B is the right answer. Congrats again Pavana and Gayatri. Thank you for your attempt. Let us go to next one. See, one more thing. See, we have a program, we have a team for stress management and career guidance, especially when you are preparing for board exam. These days students are facing a lot of pressure and a lot of stress will be there, and we have a dedicated team of psychologists and even clinical psychiatrists are there, and if anybody is suffering such pressures, we'll be having a team and we'll discuss the issues, and we'll moreover we'll guide you through all the possibilities. Many people have a limited vision, they don't know what to do after their basic course or +1 +2, and we have a team for that. Based on their aptitude, we'll suggest you and you can come and attend that such counseling sessions. Okay, so in such a scenario you can take our help, and regular sessions will be given that for all students, but if anybody is suffering, we have a facility for that. We wish to share that information also with you at this time. So one more thing, 2013 JEE Advanced question. We'll solve this question and then we'll wind up the class. Please listen, I will explain again. See here, two non-reactive monoatomic ideal gas. Non-reactive monoatomic ideal gas have their atomic masses in the ratio 2:3. It's given that atomic mass in the ratio 2:3, and the ratio of their partial pressure when enclosed in a vessel which is kept at constant temperature is in 4/3. So the ratio of the density, the question is what is the ratio of the density? Rho A by rho B. And here given that their partial pressures, see the partial pressures, the ratio of the partial pressures when enclosed in a vessel is also given, then the atomic mass is also given, then find out this monoatomic given, atomic mass is given, then find out the value of the density. Again I will give you 1 minute time, please solve. This is a JEE Advanced question, 2013 question. Try that. Yeah. Congrats. This time Gayatri did first time, then Pavana, then Gayatri, Pavana and Kavya. Okay, so congrats 3 of them, all of you. So those you attempted, thanks for that. So I will explain this once again. I mean the question I will explain because there is an important concept of partial pressure here. So then I will go to the solution. See, the concept of partial pressure is nothing but if you have a container, okay, if you have 2 gases, assume that you have gas A and B and you have certain amount of pressure is there. See, this is actually related to Dalton's law. Dalton's law is nothing but, if this, and one more thing, the partial pressure is nothing but, assume that you are removing one of the gas and if you are expanding that particular gas in the same volume, the pressure exerted by that particular species of gas is called partial pressure of that gas. Or we can say that pressure total will be equal to the sum of the partial pressure, or PA and PB. So this is the idea behind partial pressure. See, partial pressure is nothing but in a mixture of gas, the pressure exerted by individual gas is called partial pressure, or if you are removing all other species other than what we are interested, then the pressure exerted by that gas in the same volume is called partial pressure of that gas. Okay, this problem is similar to previous problem. You can do one thing, again the state equations you can write down. You already know that, see, PV is equal to nRT. You can substitute that value, the previous method you can use. So PV will be equal to M by capital M into RT we can use. So M by V, see this M by V will be density. So P into M we can multiply, that will be equal to density into RT we can write down. We can write down these equations for both cases. Okay. So PA into MA is equal to rho A into RT, and then PB into MB is equal to rho B into RT. Again is given that constant temperature, then partial pressure ratios are given, PA by PB is given 4 by 3, that you can substitute this quantity, you can substitute by 4 by 3, and we are looking for this ratio. The molar ratio is also, the ratio MA by MB is also given, so that is given as 2 by 3. This quantity is 2 by 3, this will be vanishing. So this is, how much was that, 2 by 3 into, this implies 2 by 3 into, how much was that, 4 by 3 will be equal to rho A by rho B, or we can say it will be 8 by 9 will be the right answer. If you are multiplying, you will get this will be equal to 8 by 9. So this is the right answer. Anyway, congrats for your attempt. So next we are going to wind up. Before going to that, see, we have a software to organize all the classes. It's called UNS e-learning app, and all the classes will be recorded in that. That is one of the major advantage of online class. Even if you are missing some classes, you can go back to that using your login and you will be able to see all the classes, and moreover, all the DPPs, all the question solutions, everything will be uploaded in that, so that it will be a highly organized method compared to old method. This is a very good method to recollect what, or if you want to do a revision, all things will be available, and all the document, all your records, all your progress will be recorded at the back end, and you can see your progress, and that will help you to improve. And if you are weak in some particular topic, you will be able to identify from the reports and you can work accordingly. That you can download, Android version is there and web version is also there. You can download and you can browse, you can read about the details in the Android, in the Google market itself. Okay, so Google Play. So again, we have offline centers, 2 centers are there, one in Velachery and one in Nanganallur, and if anybody wish to know more details, you can visit, you can walk into these centers and you can talk to our counselors, and we will be happy to share more information with you.